Okay, so we're going to talk about the calculus of trig functions, and I'm going to start with this graph. We're going to do it, and you could do the calculus of any function this way. This is just going to be an analysis. But this is how this idea started. So remember, when we are talking about calculus, we're talking about differentiation. We are talking about finding instantaneous rates of change. We are talking about finding the gradient. That's the main thing here. So I've got my sine graph drawn. It's all right. It's not perfect. It doesn't actually go through 0, 0. Sorry about that, but it's pretty close. What I want to know is what is the gradient at certain points. Now, we don't know the exact value of the gradient. I'll tell you the exact value, but what we do know is that this sine curve swings around here. It has a 0 gradient there because that's a minimum, and it has a maximum gradient in the middle. That's where it's steepest. And then it starts to inclinate the other way. So now it's coming back down. It has a 0 gradient back at the top again. And then it has a gradient here. It's the steepest it is, but it's negative this time. It's going down that way. So that's a negative but steep gradient, and then we get a 0 gradient again. I've got a 0 gradient here. I've got my maximum gradient there. I've got my 0 gradient here. I've got my minimum gradient, but it's still the largest possible minimum gradient. And then I've got my 0 gradient there again. And then I've got my maximum again, 0, minimum again. And if I connect that, I get cosine function. Exactly, my words. That's what I was thinking. So when you derive a sine function, the gradient of a sine function is actually just the cosine function. What does that mean? It means if I want to know what is the gradient of my sine function at, I don't know, 11 pi on 6, some random number, then I put 11 pi on 6 into cos. Cos of 11 pi on 6 is the gradient. Now that's still quite abstract. Take a step back to term 2. I want to know how fast is the water rising, my tidal movement changing at Horsehead Rock at 6 o'clock in the morning. Okay, if I built a sine model, well then I substitute into the equivalent cosine model. Now obviously your models were a little bit more complex, so there was a bit of chain rule involved in that differentiation. There's another multiplier, but that's going to tell us the gradient at that point, which in context will tell us how quickly the water is rising at different points. And that can be quite important because that can have an effect. And is a calculation used, for example, certain shipping situations where you can dock a ship, but you can't dock the ship when the water level is changing too quickly. Otherwise, you get problems. So that rate of change is really important. So there we go. That's kind of the lead-in, and it leads to this rule in orange. That's the important rule. You derive sine, you get cos. You derive cos, you get negative sine. Consequently, we get this four-way circle happening. Sine derives to cos, negative sine, so negative sine derives to negative cos, and negative cos derives back to sine, and we start the circle again. That's essentially, well, you would have to, so what is sine goes to cos, so there's a phase shift that way of pi and 2, so if you added the line inside, yes, you could do that. Yep. So then you just put your value into your original function with an addition of pi and 2. The problem comes, and I'll just show you this, and it's a good question, Baxter. If you had, say, sine of 2x. So if y equals sine of 2x, y dash equals cos of 2x times 2. And it becomes 2 cos 2x. So then, because of the chain rule implications, you get 2, which wouldn't be accounted for just in the phase shift. But it's a good point. So you could add the pi and 2 and then also multiply by your b value, because it's only the b value that's going to come out the front. Nothing else will change. That would work. Some examples. I've kind of just done one very similar to A, but here are my examples. If y equals cos 3 of x, then y dash is equal to negative sine times by the derivative of the inside function. This is the chain rule, shorthand, and that becomes negative 3 sine 3x. Done. Easy peasy. The hardest bit about this, and I think some of you have learnt this, is that you have to be able to repeat this process in term 4 next year in an external exam. So you've got to not only know how to do it now, but retain that knowledge. Y equals x squared minus sine x. Y dash equals 2x minus cos x. Done. This is just a two-part. That makes it two separate terms, a negative there. So we have x squared as a separate term goes to 2x, sine x goes to cos x. The negative doesn't affect anything. Or you can think about it like this. Negative sine x goes to negative cos x. That helps. So I've made space there and I didn't really need to. Letting me change. Okay. If y equals x squared times sine x, that's now a product rule question. And we get u equals x squared, u dash equals 2x, b equals sine x, b dash equals cos x, and y is equal to u dash v plus v dash u. So y dash equals that, therefore y dash equals, put that little cross in the middle, u dash v is 2x sine x plus x squared cos x. We can take an x out as a common factor, 2 sine x plus x cos x. This doesn't make it much nicer, but you should always be thinking, and sometimes it'll achieve nothing, but sometimes it will achieve something. And D, my last one for the first example here. This is a, what rule is this? Quotient, product, chain rule. Which one? Is that a word? Hands up if you think it's quotient rule. Okay, good. It's not a fraction. It's not quotient rule. But usually people don't confuse the quotient rule. Hands up if you think it's product rule. Hands up if you think it's chain rule. Chain rule. Good call. Okay. Now, and you put yourself in the line, and thank you for that. That's fine. There were a lot of other people in the room who called out product rule at some point in time. Just be careful here. The chain rule, in my opinion, the chain rule is the hardest one to actually identify. The easiest way to identify as a chain rule is to go, is it the quotient rule? No. Is it a product? No. It looks a bit like a product. It looks kind of like cos times e to the power of x squared, but cos times doesn't make sense. Cos, so it's cos of e to the power of x squared, and that of creates a function inside of a function. So you've got a chain rule question. So I'll do this just a reminder of the long way, because this is a bit harder. I might do it the long way for a bit of fun. I'm going to let u equal e to the x squared, and therefore y equals cos of u, and therefore dy du is equal to negative sine of u. And if you x squared, then du dx is equal to e to the power of x squared, because when we derive an exponential, it doesn't matter what's in the power. If you derive something base e, it stays exactly the same, but we have to multiply by the derivative of the inside function, which is x squared. This becomes 2x e to the x squared, and dy dx is equal to dy du times dx, and that's equal to negative sine of u times 2x e to the x squared, which is equal to negative 2x e to the x squared sine of e to the x squared. There's some mathematical norms here that you probably put your trig function at the, you probably put your polynomial function at the start. It doesn't actually really matter, but if you put anything beyond the trig function, sometimes people will take that to mean it's part of the trig function. You just got to be a little bit careful there. Putting brackets around a thing that's in your trig function though really helps. So that's also a good idea. Are there any questions on that one? Cool. This has been fun. Reggie. Well, the negative, I've taken the negative front. Yeah. It's a good point, but that negative, because then you've got to be careful with negatives, because if you leave it with the sign, it looks like 2x e to the x squared minus sine, blah, blah, blah. So you just got to be careful about how you set things out to make sure it's clear what you're actually saying, etc. And I have got one more example, example 5, which I might pause the video and let you chew on it for a couple of minutes. Go through it. Okay. So the trick here is to recognise that f of x equals tan x, but tan x can be written as sine x over cos x, and this came up in our unit circle work in term 2. So tan x is sine x over cos x. You might not remember that, but the question you should be asking yourself if you get something like this is, he's just taught me how to derive sine and cos and then given me a tan question. I must be able to find tan in terms of sine and cos. That should be if you don't quite get to that link, that's fine, but you should be thinking, I need to be able to write this in terms of sine and cos. That should be what's happening. Remember this, here's a right angle triangle, if this helps at all, and here's an angle theta, and here is the opposite, adjacent, and the hypotenuse side, and sine is equal to opposite over hypotenuse side. I've written A again. And cos is equal to adjacent over hypotenuse. And if you do sine over cos, you get opposite over adjacent, which is tan. So you can show here that tan equals sine over cos. Anyway, that's a little aside. Deriving this, though, is a case of recognising that f of x be equal to u dash v minus v dash u over v squared, where u is equal to sine x and v is equal to cos x, and therefore u dash is equal to cos x, and v dash is equal to negative sine x, and so we get f of x is equal to cos on top, u dash v is cos x times cos x minus negative sine x times sine x, all over v squared, which is cos squared, and that gives us cos squared x plus sine squared x over cos squared x. The rule that's come up, so I'll write them both down here. So they're the only two identities that you need to be aware of in math methods. If you're doing specialist math, you do a whole bunch more. But math methods, there are two. Tan equals sine over cos, cos squared plus sine squared equals 1. They both came naturally from our unit circle, and we talked about them at that stage. So this is actually now equal to f dash of x is equal to 1 over cos squared x, and we want to know when f dash of x equals 1. So that means we want 1 to equal 1 over cos x, cos squared x, which means we want cos squared x to equal 1, which means we want cos of x to equal what? Negative 1. Good. When we take a square root, it's plus or minus answer as a possibility. When does cos x equal 1? At 0. Good. So this is a cos x function. When does it equals, that's a really badly drawn cos x function, sorry about that. X equals 0. When does cos x first equal negative 1? Pi. When does cos x equal 1 again? 2 pi. So forth. There are our first three answers. Okay? Now, obviously, there are certain aspects here, if you were doing this question yourself, that you might not just be able to work out like I just did here like that. But you should be able to go in here. When you take a square root, it's always plus or minus answer. That's important when you're doing anything to do with quadratics. Once you get the plus minus answer, you just go, well, let's find the first 3 times cos x equals 1. Cos inverse of 1 equals this. Get on the unit circle, work them out. Let's find the first 3 times cos x equals negative 1. Same thing. Get on the unit circle, work it out. You've now got 6 answers. Pick the first 3 of those 6 answers. You're done. It might take you a bit longer than it's taken me, but the point is that's a complex, unfair question that is doable. The only hiccups there is if you didn't remember those identities. The last thing I'll say, though, is could you do any of this on your calculator? If you got stuck, and if this, let's say this was an active exam, you got stuck, what could you do on your calculator here? You can't do this, unfortunately. You can't do the derivative. So the calculators have changed a bit. You've lost some functionality. I don't know whether you can do it of the trig function though. You reckon you can? I'm happy to be proven wrong. So you're going to have to do this yourself. You have to know the identity. But once you get down to here, let's say you've forgotten this identity. It doesn't actually really matter, because if you want that thing to equal 1, you can sketch that thing as a graph, and then you can sketch the graph y equals 1, and you can find points of intersection. That will give you answers. Now, unfortunately, you will lose some marks, but you will gain those marks at the end. So again, it's about adapting and knowing what you can do to pick up every possible mark, even if you lose a couple in the middle. You all know how to do that stuff. That's it. That's me done. I'm stopping now.